can slowly start with the introduction. Thanks, everyone. Welcome to the new edition of the Gemini Nord Talks. Today, hi everyone. Today we are lucky enough to have here Laura Rogers. Laura was observing 2 nights ago, and it was in Chile 5 nights ago. So,
Oh, wow.
so she really wanted to come here today. Clearly, that was like her motivation in life. She's now working, actually, she's colleagues of ours. She worked with CE in Tucson on a planetary system around brown dwarfs, white dwarfs, sorry, professional bias. She got her PhD in Cambridge in 2022, and then she got her first postdoc also in Cambridge. And since December is our colleagues at NOAA Lab in Tucson. And so the stage is yours.
All right, thank you very much. I'm very excited to be here and really nice to meet you all. I'll be around for today and some of tomorrow, so I'm hoping that we get to chat because it's really nice to meet colleagues. So hi. But yeah, so I'm Laura Rogers. I'm going to talk to you today about probing exoplanetary compositions using white dwarf stars. And I will say that none of the work that I'm going to present would be possible without all of my incredible collaborators, who I've mostly listed at the bottom of the slide. I won't go through them all, otherwise that will take up most of the time, but oh, I just see it says it's being recorded. Yeah. So yeah, so feel free to take a note of their names. This is gonna work. Okay, that's working. Or has it crashed? Okay, we're gonna have to click, that's fine. Okay, so we're going to start off with our solar system. So this is a planetary system that we actually know most well. And before about the mid-1990s, these were actually the only planets that we knew of in our entire universe. And so we know that we've got our nice rocky planets in the interior regions of our system and our more gas giant planets around the exterior parts of our solar system. But how do we actually know what planets in our solar system are made from? And a lot of the time we are relying on sending probes to different planets. So for example, we can go and measure the earthquake wave speeds for different planets. And that's because waves travel at different speeds depending on the medium that it's going through. And so you can work out the general bulk composition and the interior structure of planets using wave speeds. So we can also go and conduct remote observations, and that's because a lot of the time you get outgassing from the interiors of planets, and so you can go and directly measure the stuff that's coming out of the planets to work out what's going on inside. And then you can also do a nice little measurement where you can work out the size and the mass of a body, and then you can work out the bulk density of the planets to kind of learn a bit more about the interior structure. So a lot of these rely on probes and remote observations, which are quite hard to do with exoplanets. So what can we actually really do with exoplanets? So we mostly measure the size and the mass to get the bulk density. And here you can see a mass radius plot on the left-hand side of the screen. And each one of these data points takes an unbelievable amount of time, effort, and telescope time just to measure the mass and the radius to these kinds of precisions. And so once you get your mass and your radius, you can compare it to these theoretical curves to work out what the bulk density and the interior structure of your planet is. And you can see here we've got some lines. So this is showing you your iron. And so if you had a planet made entirely of iron, this is the kind of mass and radius curve that you would expect to get. We can see that none of our planets appear to be entirely iron. Maybe that's not that surprising, but you can compare it and you can rule out that model pretty much for all of the planets that we know of in this plot. But then you can compare to things like an Earth-like density, and you can see that there's a lot of the lower mass planets that seem to have a kind of similar interior bulk density to Earth. But as you get to these higher mass planets, you're really going above even this H2O ice waterline, H2O ice line. And that's because you're getting these gaseous envelopes around your planets. So in an ideal world, what I would actually really want to do is take a planet, let's say the Earth, and hammer it up into dust. And then I want to put that dust into a mass spectrometer And then out of the mass spectrometer, it would tell me exactly what the Earth is made from.
How big is your mass spectrometer?
Exactly, massive. Huge. You need a really, really big mass spectrometer to do this. So that's a great question, because how actually big is a mass spectrometer is actually the size of a white dwarf. So you don't need to send a mass spectrometer to go to an exoplanet to work out the composition, and you can actually use white dwarfs to do all the work for you. And so this will be kind of a general theme of the talk, is let's use white dwarfs as mass spectrometers to learn about the composition of exoplanets. So what is a white dwarf? So white dwarfs are stellar remnants. They're the core of low mass stars that get left behind after stellar evolution. They're incredibly dense, so they have a mass of about 0.6 solar masses packed into the radius of the Earth. And this means that they have incredibly high surface gravities. And so you don't expect to see anything in their atmospheres other than the lightest elements, which are hydrogen and helium. And so here you can see a spectra of the closest white dwarf to us, which is Sirius B. This is a Da white dwarf, which means it's a hydrogen-dominated white dwarf, so you only see hydrogen in the atmosphere of it. And yeah, all you can see are these broad, deep Balmer features, and these are the hydrogen lines. So this is kind of what, you know, a typical white dwarf looks like, except that's not true. About 30% of white dwarfs are observed with heavy elements in their atmospheres. And so on top of your beautiful, deep hydrogen lines, you're actually seeing lines from metals, so things like calcium and iron and silicon. And so this is telling you that there has to be some kind of signs of ongoing accretion, because the white dwarfs are so dense that things kind of settle out of the atmosphere very, very quickly. And so a lot of really smart people put in a lot of time and research and worked out that it's actually exoplanetary material that's being accreted onto these white dwarfs. And that's where these signatures are coming from. So how does that actually happen? So what we think is going on is that you have your planetesimal belts that do survive to the white dwarf phase, as well as some planets. And you get these planetesimals that are destabilized, and some of them get thrown onto star-grazing orbits. So they go towards the white dwarf. And they hit this radius called the Roche radius, which is the tidal disruption radius. And everything has a tidal disruption radius. We have one, it's just, you know, really, really far inside of us. And the sun has one, but it's within the envelope. But for a white dwarf, because it's so dense, the tidal disruption radius is quite far outside of the white dwarf envelope. And so if something goes towards it, it just gets tidally disrupted and it gets ripped apart. And so this then forms a circumstellar reservoir of tidally disrupted dust. And we can actually see this based on the infrared excesses. So this is just a quick plot to show you what that looks like. So here, this is a spectral energy distribution where you've got flux and wavelength. And this bit here, this is the white dwarf photospheres. This is all of your nice optical data points align really nicely with the white dwarf photosphere. But as you start taking data, as you go to redder and redder wavelengths, you actually get excess emission. And this is from the circumstellar dust disk. And this is pretty hot. So this can be of a temperature of about 1000 Kelvin. And we often think of these to kind of looks a little bit like Saturn and its rings, but instead a smaller, you know, white dwarf with its rings. So there is also a gas that's been seen around these white dwarfs. So we know of about 100 white dwarfs that have circumstellar dust, and 21 of these actually have gas. And it's not necessarily known where this gas is coming from. Some people say that it's coming from collisions. So if you have highly energetic collisions, you can get gas. And some people say that actually when your dust is migrating inwards, it reaches the point at which it sublimates, and then you get viscous spreading in and out, and that's how you get gas disk. And so these, I just love these, I think they're super beautiful. But this is what the first example of a gas disk around a white dwarf looked like. This is a section of a spectra, and this is the calcium infrared triplet. And so what you're seeing actually is that as the gas is going around the white dwarf, you've got some of it is being redshifted and some of it is being blue shifted. And so you get these really beautiful double peaked profiles. And then you can see here, this is just a little model just to show this. And so this is pointing towards the Earth. And this is the material going away. So this is being redshifted and this is being blue shifted. And because it's a Keplerian rotating disk, depending on the distance you are from your white dwarf, you'll get a different speed of the material that's going round. And so the closest in material is actually going much faster. And so the stuff that's in the wings, this is the stuff that's moving faster, but also closer to your object. That's important for later. Okay, so then you've got your circumstellar environment with your gas and your dust, and then this material is then accreting onto the atmosphere of your white dwarf. And this is where you use it as a mass spectrometer. And so you get your lines, and here you can see this is a line for magnesium and silicon and calcium, and you work with white dwarf modelers to work out the composition of the material that's in the white dwarf photosphere. And you use that to then reconstruct the composition of the parent body that was accreted onto your white dwarf. So now we know what exoplanetary material is made from. This material then sinks to the core of the white dwarf, and for DA white dwarfs, which are the hydrogen-dominated white dwarfs, this happens over timescales of days to years. And for your DB white dwarfs, which are helium-dominated white dwarfs, this can happen over much longer timescales, more like 10 to the 5 to 10 to the 6 years, but that's still pretty quick in terms of the scale of the universe. And so far, most of the time we're seeing that the things that are accreting onto white dwarfs are pretty similar to kind of bulk Earth. They're quite rocky, they're quite dry. And so, you know, maybe the Earth's not that special after all. Well, it is, we're here, but anyway. And so what you can see here is a periodic table showing all of the different elements that we've detected so far in white dwarfs, which I think is really cool because we're doing a really good job at starting to build up a really nice chemical inventory of exoplanetary material. But it's difficult. And so most of the time, we actually only really see calcium in the atmospheres of white dwarfs. So we know of about 1,700 or 1,700 white dwarfs that are accreting planetary material. But most of the time, we only see this in calcium. But to really be able to actually build up a picture of the exoplanetary material, you need to get more elements. So you might be like, hey, you've got 1,700, but you know, we're really only dealing with like tens where we've got enough elements to get a full understanding of the planetary body. So we're greedy, we always need more data. So in summary, for the start, about 30% of white dwarfs are polluted with exoplanetary material, with more than 1,700 discovered so far. We know of at least 100 polluted white dwarfs that also have a circumstellar dust disk. We know of 21 that have a circumstellar gas disk where it's shown in emission. There's a couple more where they see absorption lines as well. And I didn't mention this, but we also see about 10 which have transiting debris. So this means that the planetesimals coming in that are actively being tidally disrupted that we can actually observe. And there's also a handful of planets. And I think with JWST, especially with all of the cycle 4 results that came out last week, people are excited about finding planets around white dwarfs. So this is going to go up within the next year. So I'm going to start off by talking a bit about the circumstellar environment. So a bit about the dust and the gas disks. And then the second half of my talk, I'm going to tell you a bit more about the pollution and what we know. Sorry.
Just, is there an observational bias that leads to the discrepancy between the polluted white dwarfs and the dust disk detection, or is there something else going on?
Yeah, definitely. So, I mean, one thing is kind of lack of data, but there's actually a lot of things that are going on there. So some of the time, your disk may actually be entirely gas. So if your white dwarf is super hot, then your tidal disruption radius will be outside of your sublimation radius. And so you might get pure gas accretion. It can also be, if you do have a disk there, it can be just undetectable. So it might be below the detection threshold. And there was a really cool paper from Jay Faruhi that came out earlier this year, where they found evidence for there being a silica emission feature, which means there is dust around it, but with no infrared excess. So that can also happen. But also because sometimes the sinking is so long, you can actually get material in the photosphere without having a circumstellar environment. So those are some of the ways. Cool. Okay. So let's start talking about the circumstellar environment. So we spoke a bit about how you've got planetesimals coming in and it's a bit violent and a bit disruptive. And so you might therefore expect to see some kind of variability in these systems. And this was actually found first by C.E. Xu and Mike Jura in 2014. And so this is just showing you the infrared part of one of the dust disks. And so what we're just looking at is the triangular data points and then the square data points. And you can see that there is a drop in flux in this region here of 35%. And then towards, I'm going to classify JHK as a near infrared and kind of 3.5 microns onwards as the mid infrared. Everyone has a different definition, so I'll just say that. So yeah, in the mid infrared, we're seeing a 35% drop in flux. And then in the near infrared, you can see there's an 18.5% drop in flux. And so this was super exciting because this actually occurred within a year. So the variability timescales are super, super short. And so everyone kind of got a bit interested in this. And so there's been a few studies of individual systems. So here's a couple of that are listed out here. But I'm going to talk a little bit about the variability surveys. So I studied the near infrared in a paper that came out in 2020. And then Andrew Swan studied the mid infrared. And at the time, only about 40 white dwarfs were known that had disks. And actually, we covered most of these in our surveys. There's a lot of overlap, which is quite interesting. So let's look at the mid-infrared. So this is kind of the Spitzer and WISE wavelengths. So this is a plot from Andrew Swan's 2020 paper. And the key takeaway here is we're looking at flux change versus baseline. And so he was looking at about 40 different white dwarfs with at least 2 epochs. And his main conclusion was that actually everything's, or most things seem to be quite variable on these kind of year-ish long timescales. And so his conclusion was, yeah, most white dwarf disks are varying and on these kind of year-long timescales. But we decided to look in the near infrared. And so here I've just highlighted this as a spectral energy distribution showing what we're sensitive to. And so we had the J, H and the K band observations, and the J and the H are still pretty consistent with the white dwarf photosphere. But the K band, this is where you're starting to get flux contribution from your disk. And so we were looking for variability in the K band where we didn't see anything in the J and the H band. And to cut a long story short, we found absolutely nothing. We found no variability in the K band. And so this was kind of interesting because these two papers came out at the same time, one saying, hey, there's no variability going on, and the other one saying everything's variable. And so it's an interesting problem to have because how do these two different surveys, which actually most of the stars were the same, how can you combine these two things together? Go for it.
Can you use WISE?
Yeah, so Andrew Swan actually, this is a section from the Spitzer one, but his other paper was on WISE and he found the same thing. So he found lots of variability in WISE and Spitzer. And they're both mid-infrared, so they're sampling this region of the spectral energy distribution. Okay, so if we just think of kind of how black bodies work, your K band is actually the kind of hotter regions. So if you just think of how black bodies go, your K band is a bit closer to the blue end, that's the hotter dust. Whereas as you get towards redder wavelengths, you're actually sampling the cooler dust, so stuff that's slightly further out. And so what we actually think is going on is that the K band, which is sensitive to this closer and hot dust, seems to be a lot more stable than the cooler dust that's further out, which is seeming to commonly vary. And so we think that there has to be some kind of physical processes stabilizing the disk or something going on in the outer regions of the disk that are a little bit interesting. And something that we also notice from this plot is, so this is showing you which systems also have gas disks. And this plot from Andrew Swan showed that all of the ones that have the most extreme variability also have gas disks. So to actually learn a little bit about the processes that are going on in these circumstellar dust and gas disks, is telling us that there's something going on. So we need to investigate this further. And so this actually inspired a, I'm going to say brave proposal that we did with ESO. And I say brave because we tried to get 2 different instruments to talk to each other simultaneously, and that is really hard. And so what we were trying to do was actually study the dust and the gas together around a white dwarf. And so we're looking at the dust by taking infrared spectroscopy. This was using Hawkeye, and we were getting JHK band imaging. And then we were looking at the gas through optical spectroscopy, and so we were getting X-shooter spectra. So I'm just going to break it down into the gas and the dust first separately, and then we'll bring them together and see if we can find any link between the gas and the dust. So firstly, with the circumstellar gas, what I'm showing you here are two different lines of the circumstellar gas. So this is one of the calcium lines, and this is one of the iron lines, and it's evolving, time is going upwards. And then this is just a stack of all of the data together. And so there's a couple of things to note, which is, I hope that you can see that. But firstly, there are two epochs, so here and here, where the calcium is going into a massive extreme outburst state. So you get this really, really big increase in your emission features. But the iron has absolutely no changes really at all for the same epochs. These are the same epochs, and you're just seeing no variation in the iron. You can also see, and I feel like it's clearer on this stack, so if we go back to our nice little Keplerian rotating gas disk, the iron is actually going to much more extreme velocities than the calcium is going. So this has got a much sharper profile and is going to much less extreme velocities. And so for this, we can actually say, well, that means our iron is coming from the closer in regions of the disk. And your calcium is therefore probably originating from a little bit further out. We can also see that the calcium lines are very asymmetric sometimes. So there are points where it actually looks like this. And we also see symmetric emission features as well. So that's telling us that there's some evolution going on in the disk. It's not particularly stable. And so if we combine all of this information together, what we think is going on is we've got an eccentric gas disk that has radially dependent excitation. And that's because the iron lines are actually, you need a much higher temperature to excite these iron lines compared to the calcium lines, which are much easier to excite. And so you end up having this hotter inner disk, which is where you're getting the iron to emission from. Doesn't mean there's not iron further out, but these particular iron lines are more sensitive to that hotter inner region. And so these iron lines are really stable, but then this calcium, which is easier to excite in the cooler regions, seems to be very dynamic. So you're seeing a lot of variability. So this is aligning with our idea that we've got a more stable inner disk and a more variable outer disk. But what about the dust? So on the left, you can see a spectral energy distribution. We're just showing two different epochs, which is basically saying, hey, it's varying. And then the main plot here is the one that's on the right-hand side. And so the key here is we're just looking at basically the emission in the three different wavebands over time. And the key thing, if it goes up, it's getting brighter. If it goes down, it's getting fainter. And so if we just look at the K-band, which is the black one at the top, you can see that there is a region where you're getting a really, really significant increase in the K-band flux. And then it's relatively stable. And then there's another point where it's really strongly emitting as well. And this is almost double in its brightness. And I will say I was super excited to find K-band variability because I spent most of my PhD trying to find it and I didn't find it. It turns out I just needed to be a postdoc. So it's just how it works. So let's actually look at them together then. So this dust and the gas. And so in the top, we've got the dust. This is the same plot we were looking at. And then the bottom, we've got the gas. And instead, rather than just looking at the profiles, we're looking at the flux that's in the lines. And so this point here, this is where you saw the crazy increase in the calcium line. And this was the second brightening in the calcium line. And you can see that it's happening at exactly the same time as the dust. And we're really excited about this for a number of different reasons. But firstly, it's really implying that there is a link between the gas and the dust. And if you remember me mentioning earlier that we don't really know where this gas is coming from, and some people thought that this was actually when you've got dust migrating inwards, you sublimate and then you produce the gas, but you would therefore expect to see an anti-correlation compared to what's seen here, where there is a direct correlation between dust emission and gas emission. And so what we think is going on is you're getting really energetic collisions, whether you've got something new coming in or you've got a really like collisional disk. You have an energetic collision that's producing a lot more dust, which means you have a high surface area, which is why you get excess dust emission. But also because you're energetic enough to vaporize your dust as well, and you're getting an increase in your gas. And so we're really starting to understand that these are quite collisional disks and learn a bit more about the variability. But we do think that we've got this kind of variable outer region of the disk, which is then therefore stabilizing as it goes inwards and then accreting onto the white dwarf. So yeah, so we're starting to get a good understanding of this in terms of the dynamics. So moving on slightly, on another thing that we can actually do with these circumstellar dust disks is we can actually start to study mineralogy. And this is coming from, if we've got a planetary body or a planetesimal that's coming inwards, it's tidally disrupting, we're actually able to take infrared spectra to directly look and kind of work out the minerals that are present in this spectra. And so I'm just showing you here two silicate-based minerals. So on the left, you can see olivine, and on the right, you can see pyroxene. And I find it fascinating because by eye, I actually find this really difficult to work out the difference between them. Yet we can do it for an exoplanetary system that's really far away. I just find that really fascinating. But a key difference with these two in terms of their formula is this is more magnesium dominated than this one. And that's just, it has 2 magnesium atoms for every silicon atom. And this just has 1 magnesium atom for every silicon atom. And so when we're taking infrared spectra of these, we can see something called a silica emission feature that occurs around 10 micron. And these two minerals look quite different if you look at their 10 micron feature. And so this is just a super quick model just to show you this. The key thing is we're sort of just looking at the shape and where most of the flux is of this mineral. And so this is just a model of a crystalline pyroxene white dwarf disk. And you can see that it's really dominated around about 9.2 microns. And so, but if we want to actually look at olivine, it looks completely different. So the strongest peak is now actually about 11.2 microns, and you get a complete shift in where most of the emission is coming from. And so just by doing some basic looking and some maths, you can take a look at some of these 10 micron features and work out the most dominant mineral based on this. And so this is just an example from CU Shu's 2018 paper where you can see flux versus wavelength, just to show you this silica emission feature. And you can model these features to work out the dominant mineral that's going on in these disks. You do, in reality, a lot of the time, you're not actually seeing something that's entirely crystalline. You do get quite a significant amorphous component, but you can still see a difference between where the peaks are lying to learn a bit about the mineralogy. And so what I'm showing here is the strongest peak versus the band ratio. And these dots here, these are all the white dwarfs. So Spitzer only observed 8 white dwarfs with its infrared spectra, and that was the best that could be done. That was like all of the ones that were possible at the time, which is pretty cool. And so what we're doing with these silica emission features is we're looking at, well, where do they peak? So where's their strongest peak? And then we're looking at kind of where is the flux? So is it more on the pyroxene side or is it more on the olivine side? So this band ratio, this is your pyroxene and this is the olivine. And then in the background, you can see some extreme debris disks as well as some things from our solar system. And so the key thing that I really like to take away from this plot is that none of the white dwarfs are sat all the way up here where they're entirely olivine dominated, but also none of them are down here and entirely pyroxene dominated. So our exoplanetary material really seems to be a kind of combination of olivine and pyroxene. But why do you really care about whether it's olivine or pyroxene dominated? And there's a number of things that are quite interesting about these minerals in particular. A lot of this is actually to do with linking to habitability. So for instance, pyroxene is much better at storing water. And what do we need water for? Life. Hey. And they also have different ways that they can recycle minerals. and like the key elements that we need for life, like the Chinops elements. And so to start to learn about the different minerals that you have in exoplanetary mantles helps you to learn a bit more about the habitability of these different systems. And something else that you can do is the white dwarfs are so kind of mind-blowingly awesome for this, because not only are you looking at the mineralogy of this material from the dust, but this dust is then accreting onto the white dwarf where you're getting the elemental composition. And so it lets you actually directly compare the elemental composition with the mineralogy. And so you can do some kind of basic models where you're like, okay, well, let's look at our olivine and pyroxene formula. So we know that we've got 2 magnesium atoms for 1 silicon atom for olivine and 1-to-1 for pyroxene. And so the kind of basic idea of in terms of planet forming is that if you had more magnesium in your gas disk that you're forming stuff out of, then you'd probably more likely to form olivine dominated minerals and maybe be less good for habitability, who knows, compared to if you had kind of less magnesium where you're more likely to form your pyroxene. And so this is just a first example, and we're hoping that, you know, JWST will get more data. But this color bar is showing your magnesium to silicon ratio from your white dwarf and comparing. And okay, there's a lot of mess here, but the one that I get excited about is GD40. So GD40 is the most olivine dominated white dwarf disk in our sample, but it also has the highest magnesium to silicon ratio. And so, yeah, okay, it's one data point, but there's a hint towards that the more magnesium rich your gas is, the more likely you are to form these olivine minerals. So my next slide is just saying the future is bright with JWST. Although cycle 4 wasn't that successful for us white dwarf disk people, we didn't get any new disks that were going to be studied. So cycle 5, we're going to keep our fingers crossed. But this is just a plot to just show that data that's coming out from JWST on white dwarf disks is beautiful. And I think given what I've been looking at with Spitzer and how hard it is to learn about the mineralogy, you can actually do proper modeling. Looking at you, sorry. We'll chat later. But you can really do some in-depth modeling of these mineralogical features to actually do a better job than just doing our basic kind of looking at where it lies in that plot. So the future is bright, not this year, maybe next year. Okay, I don't know what the time is. Oh, over there. Okay, cool. All right, so for the last part, I'm going to talk a bit about the pollution that's in the atmospheres of these white dwarfs and what we're learning about the composition of exoplanetary material based on those. Hi.
Real quick, before we move on from olivine, just because my first association with olivine is a lot of our volcanic rock here. Like our green sand beach is because of olivine. So do you think there might be a link to using the mineralogy from this study to even consider a geologic history of trends of exoplanets?
100%.
Okay.
Yeah, without a doubt. And that something that I guess is also kind of goes into that is this one here. So yes, okay, you've got olivine, but you also, there are these things that are kind of like glassy like, and things that are glasses have been through extreme kind of heating, maybe even volcanic, you know, and that's where you get these crazy peaks around 9 microns. And so I really think that, again, future is bright and there's lots to do, but I do feel like as a field, we're in the early portion of exploring this. So cool. Okay, so we're going back to our polluted white dwarfs, our mass spectrometers for exoplanets. And so I mentioned before, we know 1,700 white dwarfs that are accreting planetary material, but very few have enough elements that we can get a really good understanding of the composition. And so a big aim is to increase the number of white dwarfs that we study, but where you get lots of elements for the exoplanetary material. And so I'm going to talk a little bit about 3 papers. I'm just going to pull a couple of results out just so you can see the kind of things that we're learning about this material. So I'm going to show you a few of these plots. On the y-axis, this is just an element X, where X is across the x-axis, and normalized to silicon, and then again normalized to solar. And these elements are ordered in increasing volatility or decreasing condensation temperature. And then what we're going to do is we're going to overplot the white dwarf data points on top. And so if you were looking at a white dwarf that has accreted something that's kind of similar to like a solar-like composition or something that's quite icy, so it hasn't lost its volatiles, all of the points are going to lie basically straight across the middle of the plot. Whereas if you have something that's a bit rocky, the more volatile elements are going to have either not condensed or you're basically going to have lost them. And so you get this, what we call a volatile depletion trend. And so if you're looking at something kind of rocky, your more refractory elements are going to be sort of sitting along this line, and then your rocky stuff is going to drop off. But if we were looking at something like the core of the Earth, so something that is going to be incredibly rich in what we call these hydrophilic elements, so iron-loving elements, you're going to have an enhancement in things like nickel and iron, and your plot's going to be like pretty matching solar around here, and then you're going to get an enhancement in the middle. Whereas alternatively, if you were looking at something similar to the mantle of the Earth, you're going to get a depletion. So these hydrophilic elements, you're not going to get as much iron and nickel in your mantle. So you will see a depletion, yeah. So let's look at some data. So firstly, this is GD56. And what we can see here is all of these data points, especially the refractory data points, kind of lie along this solar composition. I've also plotted on here what bulk Earth would look like if you threw bulk Earth into a white dwarf. And so the key here is that actually most of these data points pretty much track bulk Earth. So you're not getting any kind of high trend here, you're getting this nice volatile depletion. And so we feel like this white dwarf is accreting something that is very similar to bulk Earth, creating a nice rock. And here's another one. So this is, I hope that you'll recognize, we've got a nice depletion of your hydrophilic elements. And so your lithophiles are pretty similar to being solar. And then as you get to the center, we're getting a depletion, and your iron is low, and your nickel upper limit, this is an upper limit, is actually really constraining, it's pushing it down. And so we think that this white dwarf is actually accreting a mantle-rich fragment of a larger planetary body. And so when I say that, how on earth does that happen? So in order to get a mantle-rich fragment accreting onto a white dwarf, you first have to get differentiation. And that means that your rock has to get hot enough that you get a separation where all of your iron-rich stuff kind of sinks down to the core, and your iron poor stuff stays towards the surface. And that's how you get a core and a mantle. Just like we have in the Earth, we have our lovely core and our mantle. But if you were to accrete this, you actually can't tell the difference between accreting this onto a white dwarf and this onto a white dwarf. Because from a bulk elemental composition side, you just can't tell the difference. They would just have the same amount of material. So in order to get something that's mantle rich, you have to fragment it, and you end up with these kind of mantle rich fragments and core rich fragments. And then you accrete one of these fragments onto a white dwarf. And this is how we're getting to the point where we can actually probe differentiation. And so the white dwarf that we showed adds two examples from the literature where we can actually start to build up a bit of a picture. So we're not just seeing one, we've actually seen kind of a handful now. And so that's telling us that differentiation and these violent collisions do seem to be quite commonplace. And so next I want to talk about these three white dwarfs. They're all kind of similar in terms of their abundance pattern, which is why they're all looped together. And so the key thing here is that the more refractory elements are pretty similar with being solar or bulk Earth-like. But as you get to these more volatile elements, you can see here oxygen in particular, and this actually sticks up at solar. This is not dropping down to what you would expect if you're actually accreting something rocky or bulk Earth-like. So to learn a little bit more about what's going on with these systems, we do something called oxygen budgeting. We basically count atoms. It's basic, but it works. And so what we try to do is we take our oxygen abundance and we assign it to all of these different oxides. And we put all of our oxygen into every single oxide. So we're basically building a rock. And if we have any excess oxygen left over once we've built our rock, we can learn about its kind of origin. So if you have no excess oxygen, you've built a nice dry rocky body. But if you have excess oxygen, actually the main reason that you would have excess oxygen would be in the form of water, and therefore you've probably found a water-rich body. So if we're going to do this, this kind of step, we've got, here you can see a bar chart showing your fraction of oxygen assigned, and these are just 4 different white dwarfs. So for these 3, we've built our rock, and at the end, we actually find that we have excess oxygen left over. So most likely this excess oxygen was in the form of water. So we found water-rich exoplanetary bodies. And then I like to also show this one, which was our mantle-rich body. And so when we built the rock, it was almost pretty much consistent with being all of your oxygen was assigned. So you've got, you know, a nice rocky mantle-rich body, which is quite fun. And we can also do things like look at the carbon to oxygen ratio. And so this is really important for understanding planet formation. So if you want to learn a bit about the dominant objects that you're going to form out of a disk, you're either going to be like us, silicate based, or you could potentially be carbon based. And so the carbon to oxygen ratio is really important for learning a bit about this. And so we don't have that many white dwarfs where we've got carbon to oxygen measurements yet, but I think we're doing a pretty good job. And the most important thing is you can ignore the x-axis. We're really looking at the distribution of the carbon to oxygen. And so 0, again, this is about where solar sits, and you can see different objects in the solar system. So here you've got Comet Halley, CI chondrites, EH chondrites, and bulk Earth. And overall, we're seeing that things are kind of consistent with the range of carbon to oxygen ratios we see in the Earth. But we see nothing that is truly supersolar. We see nothing that is really, really carbon rich. So this is the only one that potentially might be, but no one can agree on its temperature. So we don't think it's truly carbon rich. And even if it was, it's only just above this 0, this kind of solar line. So there is no evidence for diamond planets. Sorry to hear, but that's probably a good thing. Otherwise, Elon Musk would be beating us there. So actually, a lot of the time, using this kind of silicon-based planet formation is actually a really good thing for people to be using in their simulations, because again, we find no things that are super carbon rich. So just to summarize this part, polluted white dwarfs are mass spectrometers for exoplanets. And we actually find that in general, most white dwarfs are accreting things that are kind of dry, and they're consistent with being bulk Earth-like. We are finding these special cases where we find things that are either core-rich or mantle-rich. We found examples of water-rich systems. And then this is a really cool paper by Sina Xu from 2017, where she actually finds not just evidence for water ice, but also nitrogen and carbon ice. And so she actually says that this is a Kuiper belt-like object that's been accreted onto a white dwarf. And this is really cool. It's our only example yet of that. So I'm hoping that we'll be able to find more in the future. So in the last 5 minutes, I'm going to tell you about one other cool thing that you can do with white dwarfs. And that is actually kind of learn a little bit more about star and planet formation. And so the key question for this part is we're looking at, do planets have the same refractory composition as their star? And essentially you're asking the question as, do stars and planets form out of the same material? And so making that assumption, if they do form out of the same material, your stars and your planets should have the same composition. Great. But we don't necessarily know whether that's actually true. And you can actually use wide binaries to study whether this is actually the case. And that's because you've got your main sequence companion to your white dwarf. And because binaries are chemically homogeneous, they should form out of the same stuff. And your main sequence companion can be used to tell you the composition of your progenitor to your white dwarf. And so you're basically getting star composition, and then from your polluted white dwarf, you're getting planet composition. So you can just ask the question, are they the same? And this is something that we've been doing. And this is just an example from Amy Bonsa's paper in 2021 of a pilot study that we did. And so we're really interested here on the side of the refractory. So these are the refractory ratios, and we're just comparing star to planet. And super excitingly, we can actually see that for the refractory abundances, they do match. So there is a link between your star composition and your planet composition. And you might be like, yeah, it's kind of obvious, but like, why should we care? So let's go back to this mass and radius plot. So everyone is taking all of these mass radius measurements, and they're like, okay, well, now I need to run my interior models. Yeah, we'll pretend that made sense. So people who are trying to work out the interior structure, they have their interior model calculations. But what they do is they take their mass and their radius of their exoplanet, and they take the composition of the host star as their input to these models. And so no one actually knew whether that was a good assumption. And people are making these wild, amazing conclusions about different planets based on this, but without knowing that you can actually use the host star as the initial composition. And so our pilot study shows that actually, yeah, you can do this. This is a good thing to do. So anyone who works on interior structure modeling of exoplanets, yeah, use the host star. That's a good thing to do. But we have one data point. So we started to collect more data, and we had one paper that came out recently. So I don't really have time to go through in detail. But the key part of that one is, again, we are finding that the initial composition of those matched. And I'll just say that the recent paper that we had out actually had an astrobite come out on it as well. And so if you're interested in looking at the second example that we have, then please go and check out the astrobite. So I will just skip through this bit and put up my summary. So in summary, we started off by looking at these circumstellar disks around white dwarfs, and we found that when we looked at the dust, the further out the dust, the more variable the dust seemed to be. We also found the first ever evidence for simultaneous gas and dust emission for a disk around a white dwarf. And so we think that this is telling us there's a common origin for the dust and the gas, which we're putting down to being violent collisions in these disks. We also spoke about how we use polluted white dwarfs to probe bulk composition. So I've done 4 time zones in a week. It's polluted white dwarfs are acting as mass spectrometers to infer the bulk composition of exoplanetary material. Most of the polluted white dwarf seems to be accreting things that are quite dry and rocky, but we are finding really special examples of core and mantle-rich bodies and water-rich bodies. And we also find no carbon-rich systems, so our carbon to oxygen is tracking solar system bodies. And then finally, I spoke a little bit about this cool experiment you can do about whether your composition of your planet matches that of your host star. And I spoke about our pilot study that demonstrated that these refractory compositions do actually match. There's a lot of stuff that goes into this, so I highly suggest you go and check out the papers if you're interested. But yeah, thank you so much for listening, and I'll happily take any questions.
This was an excellent talk. Thank you so much. I'll restrain myself to 2 questions unless we have our long chat. So for the first part, I'm curious. So you said that collision could be an explanation for the mid-infrared variability while maintaining no variability in the near-infrared. I was wondering, could there be alternative explanations to that? As for, I guess I'm not very familiar with these disks' nature. Are these optically thick or optically thin disks? In the case of optically thick disks, could you be just putting surface, the variability be coming from just the emission from surface layer instead of some sort of disk evolution created variability instead of collision dominated?
Yeah.
And I'll ask the second question.
Yeah. That's a great question. And it's something that we've thought about as well. I genuinely feel like we're quite early in our understanding of these disks, and we do need a lot more data, and that will just be the answer to everything. But in terms of what we know about their optical properties, so the earliest models always assumed an optically thick disk, but there are a lot of things that are inconsistent with them being optically thick. So for example, accretion rates, but also the silica emission features. So in order to be able to see these silica emission features, you have to have some kind of optically thin dust. And so I don't think it's solved as to whether they're optically thick, optically thin, and they're probably a combination of both. But yeah, 100%. And they could be something to do with going on the surface. We thought a little bit about it, but we're a small field. And so if you know of anyone who'd be interested in kind of modeling and trying to understand this in a bit more detail, like super, super keen to get in contact. So like, let's chat.
Great, we can continue this conversation here.
Yeah.
The second question that I have was actually regarding the second part of your talk, where you were showing us very nice examples of peroxide versus olivine, where they're different stoichiometry of between the magnesium and silicon atom. These examples are the end members,
Yeah.
magnesium rich end members in the group. So you can combine also iron. to
Yes.
magnesium. I was wondering if have you considered well, I guess have you considered that aspect?
Yes, 100%. Yeah, I thought a lot about it. And the reason that I don't show it is because it's a little bit more difficult to measure iron, and particularly in the photosphere. So for the 8 white dwarfs that we have with Spitzer data, like 3 of them also have iron. And so it's not as strong of a correlation that you can do, but I've been putting in for JWST time for 3 cycles so far, trying to do this and because there are some that have, like for the ones that you can see are being like mantle dominated and core dominated, you get crazy different iron to magnesium ratios. And so you should be able to probe whether the peak is shifting redwoods because of the iron contribution. I'm really passionate about it, but no one's giving me time yet. So like, I'll go again next cycle and hope. I don't have a better answer other than I want to do it. And we can't do it with our current data. So
And maybe I was wondering, I think they look at iron, surely oxidized iron species like peptides or like iron binding having source field or stuff like that. But we can chat about this later.
yeah, okay, sounds good.
Yeah, thank you. Excellent talk. So I was wondering if there's a way you could say something, if you could measure the amount of material that was accreted on a white dwarf, you can measure the composition. Could you speculate if it was a Mars-like planet or a super Earth?
Yeah, that's a really good question. So so we can measure the amount of material, but because things are sinking out, you can't really tell how much stuff has already sunk away. If you basically look at the amount of stuff that's in the photosphere and kind of reconstruct from there, and most of the time we really are looking at stuff that's kind of like asteroid size, with the biggest probably being Ceres size. But there is kind of a question, you don't really know what your upper limit is. But having said that, there are some really cool things that you can do, and I'm absolutely going to butcher explaining this because this is work from Andy Buchan. But what he looks at is that depending on the size of your planetary body that's forming, when you're differentiating something, because of the different pressures, some elements actually act more refractory-like compared to lithophilic, depending on their pressures. And so those elements are things like chromium, silicon, and there's one other, I think it might be nickel, but anyway, you have to check his paper, it's Buchan 2021. But so you can look at the ratios of those elements and actually see like, okay, well, I know that I've got more, like the element ratios of this means that therefore it had to have been a big body because the differentiation means that this amount of material has gone into the core and I can detect this elemental ratio. So there are examples from his paper where it's likely that they're accreting chunks of a big planet. So we are really talking like Earth size, maybe a little bit bigger. But that's kind of like the best constraint we can do planetary size. But if you let me say one more additional thing, but there is an additional paper by Boris Genzicki from 2019, who found some really interesting compositions of the material that's accreted. So he actually found that not only was it accreting really volatile rich stuff, there was also a volatile rich gas disk. And he proposed that it was actually accreting the inner layers of an ice giant. So there are things you can do composition wise, but there are also things that you can do that way as well.
We can't ever speculate when the pollution started, right? Can you measure that?
With difficulty, it really depends on your accretion phase. So there are different phases of accretion. So you get this thing called build-up phase, where you can kind of directly say that the composition in the atmosphere is equal to the composition of the parent body. You can get steady state phase where everything kind of settles out because all of your elements are settling at different rates, and a declining phase, which is because they exponentially decline. So you then get different ratios. And when you look at the ratios of the elements, it can be quite obvious sometimes whether you're in build-up, steady state, or declining phase. And so when you're in something maybe like a build-up phase, you can actually kind of use the different ratios of the elements and work out when accretion started, as long as you're trusting your sinking timescales, which we're relatively order of magnitude happy with. That's probably the easiest way that you could work out when accretion started. Andy Buchan again does have a Bayesian code that can tell you a likely time of the accretion has started as well. And again, I would highly suggest going and checking out some of his papers. But again, it's from an observational perspective, it is hard.
You mentioned that there were 1,700 polluted. How many have been investigated? So that's 1,700 out of how many that have been investigated for that pollution?
Yeah, that's a really good question. I mean, it's difficult to know. I don't know what everyone's looked at. A lot of the telescopes don't necessarily have public data. But if you think about like SDSS, let's say, I think it looked at kind of tens of thousands of white dwarfs. And you get this kind of 30% like percentage of things being polluted. But the difficulty actually is the optical is not the most optimal place to look for pollution. So although a lot of, so like DESI and SDSS and all these great things, they can look for pollution, and probably tens of thousands, if not more, have been looked at for pollution. From the optical, the percentage is more like 5 to 10%. And that's mostly because you need the ultraviolet to be sensitive to that. And from the ultraviolet, about 300 to 400 white dwarfs, I would say, have been observed with the ultraviolet looking for pollution. And again, the ultraviolet's way, way higher, and that's your 30 to 50% of stuff is polluted when you look in the ultraviolet.
So that fairly high, or what seems to be a fairly high pollution rate,
Yeah.
Leads me to the next question, which is, if the pollution rate is so high and the lifetime is, I mean, even for bees is millions of years, are we safe in assuming that the pollution we're looking at is due to one object?
Oh, great question. No, of course not.
So it seems
yeah,
like a lot of our speculation is
100%.
very about the bulk properties of an object are really dodgy.
No, exactly, 100%. And this is probably one of the biggest caveats that we will always struggle with, is that it's really difficult to know whether it's one object or multiple objects. But a few things to kind of say on that is you don't need much material to show up in the atmosphere of a white dwarf. Like you just need, almost like a little sprinkle. And so although we're looking at things that are really, really old, you just need like one thing coming in every now and again to be enough. And so that could be that maybe it's just like one thing. But for something that comes up as being so like depleted in something like iron, it's kind of, it would have to be quite crazy to be able to explain that with like loads of bodies with like one mantle rich and not much else. And another thing to say is that obviously dynamics not my absolute speciality, but if I think about how things are getting destabilized, you're probably destabilizing stuff at one moment from a relatively similar place. So even if you are looking at like material that's coming in, it's probably all coming from a relatively similar place. And so even if you're looking at a few, they're probably a few similar. So this is where that stuff like the size can be a little bit difficult, and looking at total masses. But I think in general, kind of looking at composition, it's semi-okay. But it's the best we can do.
I know we're on the hour, but hopefully quick question. Does the analysis depend on from the perspective of where we're looking at the white dwarf? If something falls on the pole or on the equator? Does that matter? How does the material from something that falls in a white dwarf distribute itself on the surface of a white dwarf?
It's a great question. And I think we don't necessarily know the answer for definite, but what I can tell you, we've never seen any variability. So I spent 8 years looking for variability in the metal lines, from anything, rotation, sinking, differential stuff on the surface, like anything. And we've never seen anything, never seen any kind of variability. Yeah, so it smooths out super fast. So even if it's accreting onto the poles, it's just really rapidly distributing across the surface. And we don't see anything like that. But having said that, there's some really cool papers at the moment. They call them like the Janus white dwarfs, where some of them, like one face seems to be like hydrogen dominated, the other one seems to be helium dominated. Anyway, I wonder whether maybe there could be something in that. But like we've nothing discovered yet. So yeah.
Think we need to wrap up. Thank you again. And feel free to go to office 115 in case you have
Yes.
more questions.
Yeah, I'm around, so if anyone wants to chat.